and welcome to another tutorial. My name is Tanmay Bakshi, and this time we're going to be going over how you can build a Swift script for macOS that can automatically solve your word searches using the Tesseract OCR and OCR.Space API. So let's get right into how you can do that now. So basically what we're going to be doing today is we're going to create a shell script that can take two images. First of all, the word search itself, the matrix of letters, as well as the word list of words inside of that word search. It's then going to take those two, run them both through an OCR platform, Tesseract and OCR.Space respectively for the matrix and word list, and then those results will then be processed, sent over to Swift. Swift will run an algorithm to actually find the words from the word list in the matrix or the actual word search itself, and then Swift will output not only the locations of the letters themselves and the words themselves in the word search, but itself will actually solve the word search, highlight the words, and give them back to you. So let me tell you how we're going to be doing that. Alright, so this, I'm just going to draw out a quick diagram to take a look at how this entire application is going to work in the back end. So let's take a look at how that works. And it actually begins with the most fundamental basic blocks, of course. And so these will be our matrix and, of course, our word list. Okay, so we've got our matrix and we've got our word list. And basically what we're going to do is, now the reason I have to use two different OCR platforms is because, well, their strengths shine when they're doing their respective tasks. Because Tesseract, what I've gone ahead and done is I've disabled the English dictionary from Tesseract, and Tesseract becomes extremely good at finding this extremely structured matrix data. And in fact, what happens is Tesseract is able to return the matrix to us in the exact format that it's actually in. So let's just say we've got a 14 by 14 matrix of words or letters that contain words, the word search. What'll happen is I can actually tell Tesseract that I know this is a square of characters, and Tesseract will take out a square of characters and it'll actually give me 14 lines of data, each with 14 rows with spaces in between each row. And this is absolutely great formatting for our Swift script because it becomes so easy to parse in the code. And when it becomes easy to parse, well, it becomes very easy to work with in our word search solving algorithm. Alright, so now what we can do is we can go back over here. Now the thing is, the matrix and the word list, let's start off with the matrix. And the matrix itself, what it needs to do is go over to a program to basically help it clean up the image. Because the thing is, when you take an image with your iOS device or scan your word search, what's happening is the matrix doesn't necessarily have the best image quality. And because it doesn't have the best image quality, well, what happens is you end up with inaccurate OCR. And when you end up with inaccurate OCR, you're only able to find a few of the words in the word list. So what happens is there's this great script created by Jeff, and there will be a link to this script in the description below. And basically what it does is it cleans up your text for you. It's an amazing script. What it does is it takes the image of your text and it'll clean it up for you, and it'll make it an amazing format that OCR programs love. And so what we can do is actually send it over to his program called Text Cleaner. Technically, again, since this is a script, it's all lowercase, doesn't really matter, though the official name is all lowercase, so Text Cleaner. Okay. Now, Text Cleaner becomes a very, very crucial part, because without Text Cleaner, you end up with inaccurate OCR, and inaccurate OCR basically defeats the purpose of the entire system. Alright, now the thing is, after the image of the matrix has been sent to Text Cleaner, what happens is we need to be able to send that image that Text Cleaner outputs, which is the cleaned version of that image, we need that to be scaled up a lot until it's breaking, breaking a lot is what I'm going to say. And the reason we have to do this is because Tesseract, because of the way Tesseract has been trained and because of the way that it was built up from the ground, Tesseract loves scaled up images. It loves just raw pixel data. And so what we're going to do is we're going to use our own little, I guess you could say, our own little image magic script. And what we're going to do is we're going to rescale using image magic, which, if you didn't know, image magic is a Unix program or a Linux program that is used to resize, rescale, run filters for, and to basically do lots of magic with your images, as the name implies. And so what happens is the text cleaner output gets sent to image magic. Now, one more thing I'd like you to note here, though, is that the text cleaner itself does use image magic. It's just that it uses it for different purposes. So what we do is text cleaner will use image magic to clean up the text and clean up the image to create a very nice image for OCR. And then once we've got that great image, then we'll use our own image magic command to scale it up to 6,000 by 6,000 pixels. And so what that will do is it will give us the correct, I guess you could say, image that we will then send to Tesseract. But before I talk about Tesseract, now let's talk a little bit about the word list. Now the thing is, the word list doesn't need to be processed as much because we're using a relatively commercial OCR software called OCR.Space. And as you know, with commercial software, sometimes you get better accuracy with your OCR, and OCR.Space does not require the text cleaning. In fact, it encourages no text cleaning, because with the text cleaning, sometimes you get lower accuracy with the word list. Because of course, this is just a matrix of characters. These are actual words that we want to find. So what we're going to do is we're going to have a Python script that will actually send our word list to OCR.Space. Just going to fix my spelling there. So basically what happens is the Python script will take that image, the image of the word list, and once it has the image of that word list, it's going to then convert that to post data, and that post data will then be sent over to OCR.Space using their generic REST API. And that REST API will then, go over to OCR.Space, run their advanced algorithms and all, and then once the word list has been sent through OCR, it will be ready to be sent to the Swift script. But just before we talk about the Swift script, we have to talk a little bit about Tesseract. So what we do is we run a Tesseract script as well. And remember, this is developed by Google. And so Tesseract will then give us the output of all the characters in our word search matrix. And so now what happens is we've got this image magic output that's being sent over to Tesseract. And so now we've got both our OCR outputs and we're ready to use our Swift script. And so what we do next is we've got this Swift end. And basically the Swift end runs this really great algorithm developed by John O'Hagan. And I'll actually give you a link to where he created this algorithm in the description below. But basically the point is it's a fairly generic word search implementation, word search solver implementation. He actually created this in 2009, and what happens is I've actually taken his code, or taken his algorithm, and I've basically implemented it in Swift, in a I guess you could say more efficient or more user-friendly way. And so basically what happens, I'll tell you why it's more user-friendly in just a moment, but what happens is Tesseract will then take its output and send that over to Swift. And OCR.Space will also take its output and send it over to Swift. And once Swift has both of these inputs, that engine will start to kick in. It'll take both of them, and it'll first of all, run some pre-processing on the Tesseract script, and it'll solve some common errors that we know Tesseract does deal with. For example, zeros can easily be confused with capital O's, and so those issues are fixed conveniently with Swift. And once Swift solves those issues that Tesseract has, then finally we're able to have Swift, run its great algorithms, and once it finds all of the words in the word search, what's going to happen is Swift will give us two outputs, not just one. Let's talk about the first one first. So the first output that we're going to get from Swift is actually quite simple. It's just going to be the locations of all of our words. So basically, all the locations of where each word starts on the word list or on the word search matrix. And the thing is, though, the location isn't all we need. We want a visual way of representing it. So the user can see where their words are in a much more, well, as I said, user-friendly way. And the way I do this is actually quite simple. Well, the logic behind it isn't as simple as you might think, but it does work very nicely. And what happens is we actually highlight that matrix. So we send a highlighted, solved matrix back to the user. So basically we highlight all the locations, we highlight the actual words in the matrix and give it back to the user so that the user can actually see those results. And so what happens is Swift does give this output to you, but what happens is the location data powers this. So this is basically what's happening. As Swift generates the location output, that location output will then be used, along with just a regular Swift implementation, to actually create this solved and highlighted matrix for the user to use. And that is what we're going to be building today. And now, without any more further ado, let's go straight to the Mac part, where I'm going to be showing you how exactly you can implement this entire system behind me. Now, this was a very interesting project, so I can't wait to share it with you. So let's get right into the coding part. Alright, so welcome back to the Mac part, and now I'm going to be showing you how exactly you can implement this entire system. But just before we get into that, let's revise exactly what we're going to be doing. Now, if I go over here, as you can see, I've prepared this diagram about the architecture of the T-word search system. And so essentially what happens is, let's talk about the matrix and the word list first. These are basically our inputs to the T-word search system. What happens is the matrix will go through a pre-processing stage before it can be run OCR on, and this will involve cleaning up the text and, of course, resizing it so that Tesseract can actually make use of it. This will use text cleaner and image magic, and then once that's done, it'll go to Tesseract OCR in order to find all of the characters inside of the matrix. Once that is done, then we will take our word list and send it to the OCR.Space API through Python, and the OCR.Space API will return all the words in the word list and will output them to a file as well. Once we've got all of that information from Tesseract and OCR.Space, we then take that and initiate the Swift engine, and Swift is then going to run the algorithm by John O'Hagan, and of course implemented by me in Swift, as well as a few more extensions from others. And basically what's going to happen is, once Swift runs its algorithms, it is then going to output the locations of the words inside of the word search, as well as an actual solved word search matrix with all the solved words highlighted. Alright, so that's how our system's going to work, and now let's get to how you can build such a system. Now, one more thing I'd just like to cover really quickly is how this actually came up. And, I mean, if you think about it, word searches are technically supposed to be this sort of time-killing activity where, alright, so you've got free time and you want to solve a word search. Why not? It's something to do. But what happened is I was trying to solve a word search, and I got quite frustrated because I mean, I'm trying to find the 15th word out of all 14, and I'm unable to. And so I just want to, that sort of, I guess you could say, sparked the idea in me to say, hey, why don't we create a computer system or some sort of system, as I mentioned, that can actually take images of the word search. I don't even need to type out the word search. To take images of the word search, take an image of the word list, and then solve it for us. And that's exactly what I went ahead and did. Alright, so as you can see, this is our Swift script, and before I even start talking about all of the other parts of this algorithm, or this architecture, this entire system that I've taken from many subsystems, let's talk mainly about the Swift portion for the moment. So the Swift portion here, what this is going to do for us is it's going to do the main processing of the output from Tesseract to give output to the user as our final output. Now, inside of the Swift script, we've got this extension to the string class, and it implements this really simple Boyer-Moore string search, and this is from Ray Wenderlich, link in the description, in case you'd like to check that out. And so that's basically what we've got in this string extension, but we've also got two functions by me, and basically what these functions will do is, like, for example, the main characters function will take something like, oh, I don't know, let's just say you've got a string, and you know that the maximum value of the string can be 3 characters, like 999, alright? But the thing is, let's just say that the string is 89. What'll happen is the function min characters will automatically make this space 89 so that it'll fit in with something like 999. And similarly for something like 9, or just, 5, for example, we'll put space 5 so it fits in with 999 and 89, and it looks quite nice. It basically right aligns that text. And what happens with the min characters left is practically the exact opposite. It'll do something like, okay, let's just say again, we know that 999 is the maximum value. It'll convert just 89 to space 89. Or sorry, 89 space. And it'll convert 5 to 5 space. So that you can then have your text after those spaces and you can have everything nicely aligned. And this is used when we're giving our output to the user. And the way this helps is to, create this much better interface for the user so that they can get their output in a much better way. Alright, so after that, we've got this really great implementation of a word search solver algorithm by John O'Hagan, and of course there will be a link to John O'Hagan's Python implementation in the description below. What I've basically gone ahead and done is de-abstracted the entire algorithm, taken it from Python, converted it to algorithm form, and then once I did that, I re-implemented the entire thing from scratch in Swift. And as you can see, this is basically our Swift implementation of John O'Hagan's word search algorithm implementation from 2009 on the Programming Praxis website, and again, link to that in the description below. Alright, so what happens though is John O'Hagan's algorithm only deals with simple printing out the locations, like the row and column of the words in a very non-user-friendly way. I mean, it solves the word search, and that's great. But the thing is, we want to make this as user-friendly as possible to make sure that the users are able to actually visualize that representation, that word search being solved. And the way we do this, the way I do this, is we actually take the output from this algorithm, and then we basically go back a step, and I basically note down the row and column of every single character that's a part of a word. And then what happens is later, when we're printing out the entire solved matrix, every one that falls within those characters will then be highlighted yellow using I will just open this up really quickly, using the colors SDK or API, or the colors code created for Swift. And again, there will be a link to the colors, or the rainbow colors GitHub repository in the description below. Basically, it allows you to print out basically like bolded and styled and color text to the terminal using Swift, or to the console using Swift. And so that's what that allows you to do, but essentially the logic behind this, though, is that since we only have where any word starts in a word search, the logic behind this is that we should be able to take that starting row and column and calculate the row and column for all of the other characters in that word in the matrix through taking the direction that we know it's going in, and then of course we should be able to find it that way. So basically what happens is we note down the beginning row and column, and we append this to an array called coordinate colors. And coordinate colors will contain the row column tuples that need to be highlighted. And then what we do is we have this really simple loop, and what it does is it creates this new temp row and temp call variables. And then we loop through I in 1 to word.characters.count minus 1. Basically 1 to all the length of the word string minus 1. And basically let's just say the word is bakshi, it'll loop from 1 to 5. And so what happens is in each one, we then run a quick conditional, and we say, alright, does the direction contain the letter D? If it does, then increase temp row by 1. If it has a U in it, then decrease it by 1. And if it doesn't have any of those, then just keep, and then just add 0 to it, meaning keep it the same. Then what happens is for the column, though, we check, does the direction contain R, meaning right? If so, then add 1 to the column. But if it has an L, meaning left, then negate 1, meaning bring it back 1. And so, if that isn't there either, then do 0. Don't do anything to temporary column. Then what we do is we've calculated, what that allows us to do is after that line, we have successfully calculated the next row and column of the next character in that word in the word search. And then we append this, I guess you could say this tuple, back to the coordinate colors array, and then we just continue the cycle over and over and over again until for each and every single word we've got each and every single character that needs to be highlighted. Then what we do is we have this quick little logic here, and what this logic is going to do is it's actually going to loop through all of the results that the algorithm gives back to us. Or really not even the results. All it's going to do is loop through the actual matrix itself that it was inputted in the very beginning. And once it loops through that matrix, as it's printing out the matrix, it'll check for each row and column that it's looping through. Like for example, if it's looping through 13, 13, row 13, column 13, it'll say, alright, in the coordinate colors array, does it say that row 13, column 13 needs to be highlighted? If it says that it does need to be highlighted, then, well, what we're going to do is we're going to make it bold and yellow. And what that's going to do is it's going to allow the user to see that word highlighted so they can actually see their word search being solved. And that is how our Swift script works in its entirety. Now, of course, if you want a more detailed explanation of the algorithm, there will be another video about that very soon. There will be a part 2 about the actual algorithm behind the word search solving, and that will be out soon as well. Alright, so that's how that works, but now let's get over to a quick demo of this actual system, and once I show you a demo of the system, then we can get into how exactly you can build the other components of the system. Now what I'm going to do is I'm going to run the very simple word search script that I've created by doing /wordsearch.sh. And then I'm going to pass it matrix.png and wordlist.png. Now, if I go back to my Finder here, you can see that, as you can see, matrix.png is this matrix right here. And if I go down to word list, this is our word list for what we've got in our matrix. So that should be perfect. So now we're going to pass this, and we're going to pass our matrix, and let's see if we're able to run OCR, get accurate OCR results, and see if we're able to, of course, solve this word search. I'm going to click enter, and as you can see, it'll clean the text using text cleaner. It'll resize the text. It'll then run it through Tesseract OCR. It'll then run it through OCR.Space OCR, and just before we continue here, I'm not going to show you the bottom just yet, but first, as you can see, after the OCR.Space OCR is done, it prints out the OCR results for, first of all, the matrix, and as you can see, there are a few problems with like capital O's being classified as zeros, but don't worry, Swift will take care of that. And what we're going to do now is I'm going to scroll down. As you can see, these are the OCR results for the word list, and as you can see, the strengths of each of these OCR platforms are really shining out here. Tesseract is great with the structured data. The OCR.Space API is great with that unstructured, just word data. And then what we can do is scroll down, and as you can see, the algorithm has resulted in the rows and columns of the beginnings of these words, as well as the direction they go in. Now let's actually test this out and see if this works. Now it says that the word neural net is going left in the direction left up, meaning diagonally left and up. And it begins on 1313. Now, as you can see, this is our highlighted word search, and as you can see, it actually comes out quite nicely, and the user should be able to actually see where all these words are on their word search and then copy that down onto their physical copy. And so basically what happens is, let's just say it here, okay, 1313, let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Alright, so this is the 13th element, or the 13th the data, piece of data, or element, yes. And basically what we can do is go left up. As you can see, neural net. As you can see, this is correct. And it highlights it too, so we can see N-E-U-R-A-L-N-E-T. And so we see the word neural net, even though, again, if I were solving this word search manually, that would take me a long time. But what happens is this algorithm is able to take the OCR results, run that through the script, and then output your correct OCR results, as well as the position and the actual highlighted version. In fact, if we take a look at something like John, it's on the 13th. So we go 1, 2, 3, 4, and then over to the 13th. As you can see, John's going up, and as you can see, it says John's going up. And neither is this actually hard-coded. You can run this with any matrix or any word list that Tesseract and OCR.Space OCR have a good time classifying, and you should be able to find, if not all, at least most of the words inside of your word search. And the reason I say not all is because sometimes, there might be a few minute inaccuracies with the OCR, and then the OCR, since the OCR hasn't given the algorithm the correct characters, it wouldn't be able to assume what exactly you're talking about. But again, there are always ways to work around that, like hard-coded Levenstein's distance algorithms or something of that sort. But then again, that's for another video sometime later. Alright, so that's how that works. That was one demo. Now we've got one more demo to show you, and that demo actually has a very interesting feature where you can actually find unintentional repeats of words, and I'll show that to you in just a moment. But first, I'd like to show you the rest of the code that goes behind this entire system. And so let's actually start this off by going into the wordsearch.sh file, the orchestrator for all of this. And so what happens is, you can see, first of all, it cleans the text, and it runs this basically standard text cleaner format. Basically, it takes the first argument that it was given, and it saves the file to text clean underscore, and then the first argument it was given, so that we basically rename the file, or create a duplicate of the file that's been text cleaned with text clean underscore as a prefix of that file name. And then what happens is we then resize the text, and then we use ImageMagic's convert function, or convert command, and we give it the text cleaned image, and we resize it to 7000 by 7000 into a resized image. We then run Tesseract OCR, and we're running this on mode 6. What that means is it'll run specifically structured data. If I actually run the Tesseract command, as you can see, -PSM means specify page segmentation mode, and these are all of the page segmentation modes possible, but basically what happens is, you can see number 6 is assume a single uniform block of text, and this is exactly what our matrix is, and that's why the page segmentation mode 6 works so perfectly. We then save the output to a file called a.txt. Then what happens is we run the OCR.Space OCR. Now remember, this is a Python script, so I run the Python OCR.Space.py file. We give it the second argument passed, which is a word list PNG, and then we output whatever Python gives us to b.txt. And then once that is complete, we print out all of the OCR results by using cat, and so I do cat a.txt, cat b.txt, so that the user can actually see what the OCR results are looking like. And in fact, if we want this to be formatted a bit nicely, we could do something like this, and it would put a space between these two lines here. And then what we can do is we can actually echo out the algorithm results. And what happens here is, if I go back, as you can see, in Xcode, I've actually coded this Swift command line app. And when I build it, as you can see, it saves this word search solver as a product. When I open it in Finder, it's in a very obscure location, alright? So it's in some sort of build folder and some sort of derived data folder. We don't want to have to deal with that. So what I do is actually create a symbolic link from my Xcode build to my actual word search folder. And what happens is I make the symbolic link from that build file to the word search solver itself, and what happens is I'm able to basically create a clone of the file over here in my word search directory. And what this allows me to do is basically say, whenever I build a new Xcode build of this application, then what's going to happen is not only will it build for Xcode, that'll automatically be transferred to my word search directory as well, because it's just a symbolic link or a shortcut. And so that's how that works. And basically, we run that binary, and this is actually our Swift, and we give it the a.txt and b.txt files. And once the word search solver prints out all of the algorithm results, then we clean up by removing the extra files that we just created in order to solve the word search. And the way we do this is by removing a.txt, b.txt, the resized version of the first image, and the text cleaned version of the first image. And this will allow us to essentially clean up to the state that the directory was already in. And that is the entire code for this system. Of course, I guess you could say this was the complete code, as some of the sources that I'm using for this are open source, like Tesseract, but then again, does basically act as basically these boxes where we send in some input, they give us some output, and then we're able to use that in our architecture, in our system. And then what I do basically is, again, what's happening here is each individual building block basically of the system takes some input from the last step, gives it to the next step, and that continues on until Swift is able to take those final inputs and give us our final outputs, and does that sort of main processing, I guess you could say. The main heavy lifting, I'd have to say, is done by the OCR, because without the OCR, this would be impossible, because it's not practical to be able to enter in your word search character by character. Like if I were doing a 14 by 14 word search, I'd be entering 196 characters. That's just not possible. So the OCR does the main heavy lifting, Swift does the main processing, and all in all, we're able to get our output, which is what we really want, and in a really user-friendly way. And that is exactly what we wanted to achieve, and that's how I was able to achieve it. In fact, now I'd actually like to give you one more demo. And so if I actually go back here, as you can see, we've got this other file called matrix1, and this is another matrix that I've got here, another word search that I created. And as you can see, this is the word list for that matrix. And if I go back to my terminal, as you can see, I can actually run that word search script once more, and this time I can actually run it on matrix1 .png and wordlist1.png, and these are different files than the ones that we were using last. And so what's happening again, it's cleaning the test, resizing it, Tesseract, OCR.Space. It's then going to run the algorithm, as we know, once it comes back from OCR.Space. Again, sometimes OCR.Space does take a little bit of time due to the fact that, again, it is a REST API, and it really depends on, factors like internet speed, API uptime, etc., to ensure that OCR.Space is functional. Then again, what we can always do is cancel that, or never mind, right as I was about to, it is done, or actually, no. Unfortunately, OCR.Space has not yet returned our results, but it's alright. Let's run this word search once more, and let's see if OCR.Space is able to return our results. Now, in just a moment here, we should be able to feed in our image to OCR.Space, and OCR.Space will be able to reply to us. Now, what I'm going to do is I'm going to be right back in just a moment once OCR.Space is done processing. I'll be back in just a moment. Alright, so my internet had a little hiccup there, and it wasn't able to communicate with OCR.Space exactly perfectly, so let's just go back to the terminal here, and this should work now. So if I just go back to word search, and if we rerun the script again, no code changes, just a quick internet hiccup. So if we just run, as you can see, it returns the correct results, but if I go back, as you can see, our OCR results are great. We got a correct word list. We have one IBM in this word list, though. So, I mean, I included the word IBM in the word list. But the thing is, if you scroll down here, for some reason the algorithm is returning 2 IBMs. Okay? And so this is one of the great things about this algorithm. What happens is if I scroll down, unintentionally, there are 2 IBMs inside of this word search. If you take a look here, the first one here that goes right down, okay, it was 7-1 right down. This is IBM diagonally, alright? But the thing is, as you can see here, we've got some words, NVIDIA, and we've got Tanmay, and after NVIDIA we've got bakshi, but that's not relevant to this. Now the second I in NVIDIA and the first M in Tanmay, they've been bridged using a B in one column, and so unintentionally I've got another IBM linking these two words. And what happens is the word search algorithm is able to find that word. And so unintentionally there was another word that was included in this word search which I most probably wouldn't have found, but the word search algorithm, the word search architecture, the system, was able to find it. And that's just one of the great features of this entire network. But apart from that, as you can see, it found words like deep learning, it found CUDA, it found Twilio spelled backwards, it found convolutional, it found Apple, it found, of course, IBM, NVIDIA, Bakshi, Tanmay, and, of course, another IBM. And so that is how you can build your own word search solver. Of course, this T-word search solver architecture, this entire system that includes so many different great projects, all put into one great little system that can basically analyze and then solve your word searches for you. And of course, this was an absolutely really fun project to work on. All the source code will be down in the description below so that you can check that out and use it yourself. Alright, so thank you very much for watching today. That's going to be all for the video. I really do hope you enjoyed and you were able to learn something, and of course if you did, please make sure to leave a like down below. And of course if you believe this could help anybody else you know, like your friends or family, please make sure to leave a like there as well. And of course, as I said, share the video as it really does help out a lot. But apart from that, if you have any more questions, suggestions, or feedback, leave them down in the comment section below. Email them to me at taggymanny@gmail.com or tweet them to me at taggymanny. Alright, so that's going to be it for this video, but if you want to see a lot more content like this, and of course you want to show your support for this channel, please make sure to subscribe as well, as it really does help out a lot. And of course, if you'd like to be notified whenever I release new content via email and Google notification, please do make sure to turn on notifications by clicking the little bell icon beside the subscription button below as well. Alright, so thank you very much for watching today. I hope you enjoyed. Thank you. Goodbye.